Section 9.4 is on two variances or standard deviations, and we're looking at the inferences involved in those. The hypothesis test for two variances or standard deviations uses an F-test, and the requirements of this test are that the two populations are independent, the two samples are simple random samples, and each of the two populations must be normally distributed regardless of the sample size. This is a very strict requirement. The test statistic for hypothesis tests with two variances is that the null hypothesis is that the two population variances are equal, and the F-test, which I'm not too sure why I have a minus symbol between there. The F-test takes the sample variance of the first sample divided by the sample variance of the second sample, where the first variance is the larger of the sample variances. So we would just manipulate the data so that's the case. We will compute the p-value and the critical value with SAS. The critical f-value is determined by the significance level alpha, the numerator degrees of freedom, so degree of freedom of n, the first sample size, minus 1, and denominator degrees of freedom by the second sample size, minus 1. The two-tailed test divides alpha in half, and one-tailed test uses just alpha as is. The F distribution itself, for two normally distributed populations with equal variances, the two population variances are equal, the sampling distribution of the test statistic F equaling to the first variance divided by the second variance is the F distribution. And if you repeat the process of selecting samples from two normally distributed populations with equal variances, the distribution of the ratio of the first variance divided by the second variance is the F distribution, which looks like a skewed right distribution. And it's not at all symmetric. The F-test requirement of normal distribution the F-test requirement of normal distributions is quite strict. Examine the distributions of the two samples using histograms and normal quantile plots, and confirm that there are no outliers. Otherwise, it is heavily suggested not to use this, since it's a very strict requirement. There is a different F distribution for each different pair of degrees of freedom for the numerator and denominator. The F distribution is not symmetric, values of the F distribution can never be negative, and the exact shape of this F distribution depends on the two different degrees of freedom. Again, it's a skewed right distribution. To interpret the value of the F-test statistic, if the two populations have equal variances, the ratio of this first sample variance divided by the second sample variance will tend to be close to 1. Because we are stipulating that the first variance is the larger sample variance, the ratio of the first variance divided by the second variance will be a large number when the first variance and the second variance are far apart in value. Consequently, a value of f near 1 will be evidence in favor of the two population variances equal, but a large value of f will be evidence against the two variances being equal. So, for example, when investigating a relationship between birth weight and IQ, researchers found that 258 subjects with extremely low birth weights, less than 1,000 grams, had Wechsler IQ scores at age 8 with a mean of 95.5 and a standard deviation of 160.0. For 220 subjects with normal birth weights, the mean IQ score at age 8 is 104.9 and standard deviation is 14.1, based on data from neurobehavioral outcomes of school-aged children born extremely low weight or very preterm in the 1990s. By Anderson et al. In the Journal of American Medical Association, volume 289, number 24. Using a 5% level of significance, test the claim that babies with extremely low birth weights and babies with normal birth weights have different amounts of variation. we can see based upon this that these would be independent of each other, these samples. Why is that? Because one birth weight should have absolutely no impact on the other. Pendant. So they're independent. We're going to assume that the populations are normal, since we were only given summary statistics here. We wouldn't really be able to check any quantile plots or histograms, unfortunately. But, from what we have here, we are going to let the first variance equal 16.0 squared, and the second variance equal to 14.1 squared. Again, to make sure that the higher variance is the first one. The null hypothesis for this is that the two population standard deviations are equal. The alternative is that they are not equal. And this uses an alpha of 5%. So, because we were given these summary statistics, and let me just show the Excel document with this in there. We need to put it into a Excel document like this, where we note the two populations, low birth weight, normal birth weight, and we need the statistics of sample size, mean, and standard deviation, which we were given in the problem described in here, and then those different values. But let me just very quickly close that and upload into there the birth weight data set, which I never uploaded in there. Awesome. Okay. Let me very quickly put that in there. And let us see. Okay. So now we should just be able to reload this, and it should be in there. Yes, it is. Okay, good. And I'm just going to change this to be the name birth weight, just so we know what we're looking at. Okay, the code that we're going to use for this is once we're actually selected, proc t-test data is equal to work dot birth weight. We're using the t-test because I don't know if you took notice on the other videos from this particular unit, but this does give us the test for the variances as well. So work dot birth weight, alpha is going to be equal to 5%. The test is going to be the difference. And the side we're going to use for this is going to be 2, due to the fact that we want this to be not equal to each other. And now we could specify that the null hypothesis is equal to 0, but again, that is that's assumed. You don't technically really need it. The class for this, based upon the way that this data set was coded in the file, we call this birth weight and IQ. So birth weight is the class, and the variable is IQ. And then we're going to run this. Let me first get rid of this, and we're going to run this. And then after a while, it brings itself up here. We want the equality of variances section down here, which will give us an F value. It'll give us an F value of 1.29 and a probability here of 0.0537. So let me write that out very quickly. Our F value, which is when we took these two variances and divided them. So let me actually write that out. 16.0 squared divided by 14.1 squared. This value we computed was 1.29, pretty close to 1. And the p-value is equal to 0.0537. And we can write out what this means. So at the 5% level of significance, right, the p-value there is greater than 5%, so there is not sufficient evidence to support the claim that the two populations have different amounts of variation, meaning that they are essentially speaking the same. And an alternative method for this, since again it's a very strict normality requirement, one of the alternative methods is this count 5 method. It's a relatively simple alternative to the F-test and does not require normally distributed populations. If the two sample sizes are equal, and if one sample has at least 5 of the largest mean absolute deviations, or MAD, then we conclude that its population has a larger variance. And another alternative method is this Levine-Brown-Forsyth test, also known as the modified Levine's test. This is robust against departures from normality. This test transforms each set of sample values, where each x value is replaced with the absolute value of x minus the median, and then a t-test is conducted of equality of means for independent samples. Since the transformed values are now deviations, the t-test for equality of means is actually a test comparing variation in the two samples. Let me know if you have any questions or concerns. Thank you.